Hi guys, I just wanted to go over your lab 4 with you because I wanted to make sure you understood number 1, what I meant by drawing a free body diagram, and also I wanted to talk to you about the results of this lab. Alright, so starting this next week, you guys are going to be doing some homework problems where you're going to be asked to draw free body diagrams. I'm going to add some extra videos for you to show you how to do that, to supplement the instruction the book gives you and the videos from the book as well. But let me talk to you about what a free body diagram is. A free body diagram is a diagram that illustrates all the forces acting on a mass. When you have two masses, you need to look at each mass separately. So here we have the hover mass, and the hover mass has its weight acting downward. It has its normal force acting upward, and they're canceling each other out, so it's in equilibrium here. So I drew these vectors as arrows, and they are about the same length, showing that they cancel each other out. The block is being pulled on by the string, so this horizontal vector is the tension. At the same time, we have this other mass here, and this other mass is hanging, and it's actually the one that's going to drive the whole system. So it has a weight of its own, and it has tension acting on it. I want to mention to you that the two tensions are equal and opposite to each other, right? I mean, this pulley just takes this upward tension and pulls it around so that it's pointing towards the west. And so it's equal and opposite. They cancel each other out. So they're really not really important here. What is important, though, is that there's one main force driving both of these masses. So when we write a net force equation, we start out with the total force equals the mass times the acceleration. The total force acting on this is just the weight of the hanging mass. The mass of the hanging mass times gravity. And that is going to cause the total mass of the system, because they're connected by a string, to accelerate. So the mass on the table plus the hanging mass is going to accelerate. So that's just m total times the acceleration of the system. They both will have the same acceleration. The other thing I want to mention to you is when I ask you for what the net force is, you guys are getting kind of semantically confused. Gravity is an acceleration. So the force that's causing this to accelerate is not gravity. It's the force due to gravity. It's the weight of the hanging mass. I did not take off points for that because, you know, that's a semantic thing that we have to consciously think about. So the other part of this lab was that you were going to, you have two different experiments. In the first experiment, you're going to change the mass of the hover mass and the hanging mass as indicated. In other words, you'll start out with 900 grams and 100 grams and 800 and 200, but notice that the total mass is always staying the same. So what we're really looking at is the effect of the difference in mass on the acceleration of the system. So, and that is because if you look in your book, they derive the equation for this type of modified Atwood. And the equation for the acceleration of the system, if you do a little bit of magic algebra, you start with m on the table times gravity equals m on the table plus, m times m of the hanging mass times gravity equals m of the hanging mass plus m of the table. If you do a little bit of algebra, you can reduce that equation down to being the difference in the two masses divided by the total mass times acceleration of gravity gives you the acceleration of the system. So what we want to see here is we are actually not changing the total mass, but we are changing the difference in mass. So the change in the difference in mass, the bigger the difference there is between the masses, the bigger the acceleration will be. That makes sense because you think about it, the more weight there is you know, accelerating this, or the more mass there is pulling, you know, hanging on this, the more weight there is, then the more acceleration there's going to be. So you should have found that as the difference in mass increased, like 900 minus 100, right? or 800 minus 200, or 700 minus 300. These are the differences in the two masses. That you should have seen, with the bigger difference between the masses, the more acceleration there was. In part 2, instead of keeping a constant total mass, we actually increase the total mass. So the change is always a difference. And so we increase the total mass. And as we increase the total mass, you should have seen that as the total mass gets bigger, the acceleration of the system gets smaller. Now that makes common sense, because if you're always using the same hanging mass, right, and your total mass is getting bigger and bigger, then you're always going to have less acceleration, because you're trying to accelerate more and more mass with the same force. Hope that explains things. I'm going to post this video for you in the announcements.